Good morning, dear students. Welcome to the third part of the problem session. We are doing exercises from chapter 1, Electric Charges and Fields. If you haven't watched the first two classes, please see the description. The links are given in the description of this video. In the last two sessions, we have solved 12 questions. Now we are going to consider the 13th question of our NCERT textbook. Suppose the spheres A and B in exercise 12 have identical sizes. A third sphere of the same size but uncharged is brought in contact with the first, then brought in contact with the second, and finally removed from both. What is the new force of repulsion between A and B? This question is the continuation of question number 12. And in question number 12, you are given the distance between the two spheres as 50 centimeters and the charge on each 6.5 into 10 raised to minus 7 coulomb. I think now you are able to do all the problems by yourself. And as I told you before, this class is only for your reference. If you have some doubts, you can clear. So, the second part of the question is very important. You have to read it very carefully. See, the third sphere, you are bringing a third sphere. It is of the same size, but it is uncharged. It is brought in contact with the first, then brought in contact with the second, and finally removed from both. What happens if two spheres are brought in contact with each other? We know the charges will be shared. Both are identical in size. So first sphere is charged. A is charged and the third which you are bringing is uncharged. So what happens naturally? See the figure? You are bringing the third sphere, C. Okay? It is brought in contact with A first. What happens? The charge on A will be shared between A and C equally. C has no charge now. So A has some charge, 6.5 into 10 raised to minus 7 coulomb. So A and C will share the charge equally. So the charge on each, QA and QC, will be 6.5 into 10 raised to minus 7 divided by 2. You will get 3.25 into 10 raised to minus 7 coulomb. That is the charge on A and C now. Now, this sphere C is now brought into contact with B. See the figure? C is now in contact with B. Then what happens? The charge on B and C will be equally shared. So, after sharing the charge between B and C, QB and QC will be equal to QB plus QC by 2. B has some charge, C also has some charge. So, when they are brought in contact with each other, these two, the total, the sum of these two charges will be equally shared. So, you have to find out QB plus QC divided by 2. So, you will get the value as 6.5 plus 3.25 into 10 raised to minus 7 all divided by 2. You will get 4.87 into 10 raised to minus 7 coulomb. And now it's easy. You just have to apply the formula F equal to K Q1 Q2 divided by R square. Substitute the values and calculate. You will get 5.69 into 10 raised to minus 3 Newton. Okay. Now, question number 14. Figure shows tracks of 3 charged particles in a uniform electrostatic field. Give the signs of the 3 charges. Which particle has the highest charge to mass ratio? In the figure you have a uniform electric field and you have 3 particles. In the question you are given these 3 are charged particles and you have to find out the signs of these charges. In the figure, it is clear that the electric field is applied by using two plates, charged plates. The upper plate is positively charged and the lower plate is negatively charged. See, the particle 1 bends towards the positive plate, right? So what will be the charge of particle 1? It bends towards positive plate. That means it should be of negative charge. Then particle 2, that also bend towards positive plate. So that also is negatively charged. Now what about particle 3? Particle 3 is bending towards a negative plate. Okay, the lower plate is negatively charged. And particle 3 is bending towards the negative plate. So it is clear that particle 3 is positively charged. We know only unlike charges attract. So the charge which is moving towards the negative plate, it should be positively charged. So particle 3 is positively charged. Now come to the last part of the question. Which particle has the highest charge to mass ratio? Now you see the figure, you understand the figure properly, you get an idea about the deviation undergone by all the three particles. Okay, from the figure it is clear that particle 3 is most deviated. Compared to the other two particles, particle 3 is most deviated. So, you have the formula displacement S equal to ut plus half at square. You can assume that the initial velocity, maybe let it be 0 for all, or it may be moving with uniform velocity. It's not given in the question, doesn't matter. We'll find out the acceleration. Acceleration, as you know, it is E divided by m. How is it E? E, charge, capital E, electric field, by m, mass. So that is the acceleration. See, displacement, suppose all the three are having same initial velocity u. So the displacement is more for the particle with large value of acceleration, right? S equal to ut plus half at square. So S is more when or for the particle with large acceleration. And acceleration is given by E by m, where capital E, the electric field intensity, is same for all. Then S must be more for the particle with large E by m, right? S must be large for particle with large E by m, because S is large when acceleration is large. Acceleration is large when E by m ratio is large. So you can conclude that the particle with large E by m ratio has the most value for displacement, the highest value for displacement. And from the figure you know that the particle 3 has undergone the largest value of deviation, large displacement. So acceleration must be large for particle 3 and therefore E by m ratio is more for particle 3. Okay. Now question number 15. Consider a uniform electric field E equal to 3 into 10 raised to 3 I cap Newton per Coulomb. What is the flux of this field through a square of 10 centimeter on a side whose plane is parallel to the y side? B part, what is the flux through the same square if the normal to its plane makes a 60-degree angle with the x-axis? You are given the electric field intensity E, then you are given the square, the side of the square 10 centimeter, and electric field is along x-axis because I cap is there. I cap shows that the electric field intensity is along x direction. Another factor given is that the square whose plane is parallel to YZ plane. The square is in the YZ plane. Electric field is along the x-axis. Now you can imagine the situation. X-axis, that is the direction of electric field, YZ plane. See, x-axis is normal to YZ plane, right? You are familiar with the Cartesian coordinate system, x, y, z. X-axis is normal to YZ plane. Then what about the flux? You get maximum flux, right? Come to the solution. So, coming to the first part, A, you are given the electric field intensity E. In flux you have to find out. And the part A, you are given that the square is or the surface is in the YZ plane. So, see the figure in the YZ plane. That means it is normal to the x-axis. So, you have maximum flux. X-axis and YZ plane are perpendicular to each other. So, the flux is E dot S equal to ES cos theta. Theta is 0 because x direction and area vector both are parallel. So, theta 0. You have maximum flux. So, flux phi equal to 3 into 10 raised to 3 into 0.1 into 0.1. You will get 30 Newton meter square per coulomb. Now, coming to the second part, you are given that 60 degree is the angle, okay, between the surface and the electric field. Electric field is again along x direction, and see how the surface is now. See the figure. The surface is now at an angle 60 degree, or the surface is now at an angle with the electric field. Now it is not, the electric field is not normal to the surface, or you can consider an angle of 60 degree between the direction of electric field and the area vector. Okay, vector E and vector S are at an angle 60 degree. So, flux is ES cos 60. Substitute the values. Cos 60 is 1 by 2. And area, it is a square. So, area is A square. 0.1 into 0.1. So, you will get 15 Newton meter square per coulomb. Now, we will pass on to the next question. Now, question number 16. What is the net flux of the uniform electric field of exercise 15 through a cube of side 20 cm oriented so that its faces are parallel to the coordinate planes? So, you are given E in the previous question. This one is the continuation of that question. You are asked to find out the net flux, okay, through a cube, and side of the cube is given. It is oriented so that faces are parallel to coordinate planes. Coordinate planes you know, okay, x, y, y, z, x, z, okay, 3 coordinate planes. And the faces of the cubes are parallel to the coordinates planes. And you are given in the previous question, the electric field intensity is acting along the x-axis. So, x-axis means which plane you have to consider? The plane which is normal to x-axis, where you have maximum flux. For the other two planes, electric field and the plane is parallel. Okay. So, E dot S equal to ES cos 90. Cos 90 is 0. So, you just have to consider the two planes which are perpendicular to the x-axis, means in the YZ plane. In the YZ plane, you have two surfaces which are perpendicular to the x-axis. So, phi equal to q by epsilon 0, it is equal to 0. Why it is equal to 0? The total flux through the cube is equal to 0. Why? Because the number of field lines entering the cube is equal to the number of field lines leaving the cube. Right? How many field lines are entering through one face? The same number of field lines are passing out through the other face. You are considering the cube. Imagine the three-dimensional situation. Okay? And the electric field is along x direction. So if you have some field lines entering the cube through one face, the same number of field lines will go out through the other face. So what is the net flux passing through the cube? It is equal to 0. Okay. Now question number 17. Careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is 8 into 10 raised to 3 Newton meter square per coulomb. What is the net charge inside the box? Okay, you are given a black box. Net outward flux through the surface, that is given. You are asked to find out the net charge. Now, second part of the question, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? Hope you understood the question. In the first part, you are asked to find out the net charge. In the second part, you are given that the net outward flux is 0. Then can you conclude that there are no charges inside the box? Remember our previous question. Okay. The number of field lines entering equal to number of field lines going out gives you net flux equal to 0. Now, flux equal to 0 does not mean that there are no charges. Then what does it mean? We'll come to the conclusion. You are given phi epsilon 0. You have phi equal to q by epsilon 0 by Gauss's law. Q equal to phi into epsilon 0. Now substitute 8 into 10 raised to 3 into 8.85 into 10 raised to minus 12. You will get 70.8 into 10 raised to minus 9, or Q equal to 0.07 microcoulomb. Net flux 0 does not mean that the charge inside the box is 0. It means that the net charge inside the box is 0. Okay, it is very, very important. The net flux in a box equal to 0 means the net charge inside the box is equal to 0. What does it mean? There can be a dipole inside the box, right? In the case of a dipole, what is the net charge? Net charge is equal to 0. But there are two charges, a positive charge and a negative charge, which are equal in magnitude. So, there are charges inside the box, but net charge inside the box is equal to 0. Then the flux may be 0. Or the flux will be 0. If the net charge is equal to 0, the flux will be 0, but it does not mean that there are no charges inside the box. Clear? Now, question number 18. A point charge plus 10 microcoulomb is at a distance 5 cm directly above the center of a square of side 10 cm as shown. What is the magnitude of the electric flux through the square? You are given, think of the square as one face of a cube with edge 10 cm. So, you are given one square and directly above the center of that square, you have a charge. The side of the square 10 cm, charge is at a distance 5 cm. And you are asked to find out the flux through the square. What is the flux through the square? And you are asked to imagine that this is one face of the cube. So you can imagine that this charge Q is inside a cube. Okay. Then what is the flux? So in the case of a cube, let the total flux be Q by epsilon 0, not in the case of a cube. In the case of any surface which encloses charge Q, that's what Gauss' law says, right? If a surface encloses a charge Q, the total flux is Q by epsilon 0. Now the surface is a cubical one, and we know the cube has 6 faces. So the total flux passing through all 6 faces of the cube equal to q by epsilon 0. And you are given one face of the cube. Okay, you are given a square and you are asked to imagine that this square is one face of the cube. So how much flux will pass through that square? It's clear. It is 1 by 6th of the total flux. Okay, so because there are 6 faces, through all the 6 faces you have flux q by epsilon 0. So what is the flux through one phase? It is 1 by 6 of the total flux. So phi, the flux through one phase, equal to 1 by 6 into q by epsilon 0. Substitute 10 into 10 raised to minus 6 by 6 into 8.85 into 10 raised to minus 12. You will get 1.88 into 10 raised to 5 Newton meter square per coulomb. Okay, hope all the problems are clear to you. And if you have any doubts, please comment your suggestions also. Hope you have done all the exercises given in the textbook, and we'll meet with the next video soon. Please subscribe the channel and press bell icon for notification. Thank you.